Okay, Newton's second law. So let me describe how to think about Newton's second law. It's simple, but is really can be used in a sort of complex way. So the second law says that acceleration is equal to the ratio of the forces over the mass, right? So it's a pretty simple equation, but how we use it really can get a bit more complex. And I like writing it this way. So sometimes people will say force is equal to mass times acceleration, which is mathematically valid, but I like to think of it this way because we're dealing with acceleration. And it reminds me that if I have zero force, I still have mass, right? So that's not going to be zero, and I just have zero acceleration. So a few complexities. So one that, remember, we separate dimensions here. So I'll have my force in the x direction. I'll have my force in the y direction. And this is going to be true. So I can get acceleration in my x dimension is going to be the sum of the forces acting in my x direction divided by that mass. And this acceleration in my y direction is going to be the sum of the forces acting in the y direction divided by the mass. So that's one part of it. The second part of it is one part of it is that we'll separate into dimensions. Second part is that internal forces will end up canceling. So we'll take a look at a couple of examples of this, and hopefully that'll make more sense. So again, we're looking at things that will have unbalanced forces. Will have a net external force acting on them. So a couple of quick examples. So let's look at this one. So here I have two boxes and I'm pulling with some force. These are connected by some string, right? So important, they're connected by a string, so they're physically attached to each other. And I'm going to pull on this. For right now, I'm going to forget about friction because I don't feel like dealing with it. So I can look at this, right? I can look at acceleration for box 1, and I can look at acceleration for box 2, or I could look at acceleration for my whole system. And all of these, we're going to use the same equation, but so the forces are going to be a little bit different. So let me draw a force diagram. So here's force diagram for 1, right? So what do I have going on here? Well, I'm going to have the mass of 1 times gravity. I'm going to have a normal force, and those will be equal and opposite, so those should cancel. Like sitting on this surface, it's not accelerating in either direction, up or down. It's going to be experiencing some tension pulling it in this direction. When we think about box 2, what's this experience? Well, it's experiencing some force that's being applied. It's also experiencing a normal force acting on box 2. I should maybe say 1. And it's also experiencing its force of gravity acting on its mass, and those two should cancel. And lastly, it is also applying some tension to haul box 1 along with it. So notice my applied force must be greater than my tension for this to accelerate. So and the way I think about this is that some of that force is consumed in changing the inertia of this object, and the remainder of the force gets transmitted. So let me think about my whole system now. So altogether, my system, well, what do I have? I have box 1 and 2. And what do I have in my system? Well, I'm going to have the normal force of 1. I'm going to have the normal force of 2. I'm going to have M1G. I'm going to have M2G. I'm going to have my applied force. And what else do I have? Well, I've got these two tensions, right? So I'm going to have tension going in this direction and tension going in that direction. And these are going to cancel when it comes to time for it. So those are internal forces, and internal forces will always cancel. So when we talk about an object and the forces acting on an object, we only worry about the forces that are external. And you think about this, right? If you're driving in your car and you push on the dashboard, your car's not going to go any faster. So right? You push against the dashboard pushes against you. There's no net effect. So anyway, let me walk through some examples of this. So we can use this just looking at box 1. We can look at this. So what are the sum of the forces divided by the mass? Well, let me think about this. So I've got two dimensions to choose. So I have my vertical dimension, which is not so interesting, right? So forces are going to cancel. My acceleration is going to be 0. And I have my horizontal dimension. So in this case, this is going to be my tension that I get divided by the mass of 1. I'll do the same for box 2, but notice now my sum of my forces, again, my vertical dimension is not so interesting, so I'm not going to worry about that. I could write that separately. My horizontal dimension is the one I'm interested in. So here in my horizontal dimension, my sum of my forces in my horizontal dimension divided by the mass, it's going to be what? Well, I've already decided, because I made this tension positive, I decided this is the positive direction. So this tension going backwards is going to be negative, and this applied force is going to be positive. So I have my applied force minus tension, and divide that by mass. And notice this is what I was trying to say before. So some of that force that we apply gets consumed when we change the inertia of an object. So if we get something to go faster or to change directions, that consumes some force. And so the amount of force it consumes is the difference between that and the tension that it passes on. So notice that for my system, though, so my system now is going to be some of the forces. And again, I'm going to be worried about the horizontal dimension because that's the interesting one. And this is going to be equal to, what do I have for my system now? Well, my tensions cancel. I'm just left with my applied force. So my applied force divided by my total mass. My total mass is going to be m1 plus m2. So notice I've ended up with three different equations, right? And this gives me a system of equations. I can figure out what one force is. If I wanted to know tension, I could do that. But also importantly, because these are linked, because these are connected by a string, that all of these accelerations are going to be equal, right? So acceleration 1 is going to be, that box 1 is going to be accelerating just as fast as box 2, and that's going to be moving as fast as my whole system. So in forces, our connector is often the acceleration of two objects. So let me throw one more wrinkle in there, and then leave you to think about it a little bit. So in this case, I have two boxes and a pulley, right? So let me draw two force diagrams. So I'm going to have a force diagram for 1. So what am I going to have for 1? I'm going to assume this is frictionless because I don't feel like dealing with it, right? So I'm going to have tension pulling in this direction. I'm going to have my normal force on 1 pulling up, and I'm going to have mass of 1 times gravity pulling down, and these two are going to be equal and opposite. What do I have for block 2? Well, for block 2, right, I have the mass of 2 times g, and pulling up, I'm going to assume this is a massless frictionless pulley, which means that this tension is pulling up. Right? Are these two equal? Well, only if it's stationary. So the complexity is here. So here I'm interested in my horizontal dimension, and here I'm interested in my vertical dimension. So I'm going to be careful how I phrase this. So what I'm going to do is I'm going to make one dimension, which is the direction of motion. So I'm going to say this direction of motion is positive, and I have to be consistent and say this direction of motion is also positive. And the pulley acts to change the direction of the force, so it's okay. I can think of it just as rotating this diagram 90 degrees. So let me go through the steps of this. So I'm going to have my acceleration acting on box 1 is going to be the sum of the forces acting in the direction of motion. And that's what I'm interested in. Acting in the direction of motion, which is my tension, divided by m1g. My acceleration acting on box 2, or this resulting on box 2, is going to be the sum of the forces. Notice now that my direction of motion is positive. I have to be consistent between these two. So I'm going to have m2g as being positive. Oops, that should be m1 at the bottom there. And m2g is positive, and now tension is negative, and I'm going to divide this by m2. And my system altogether, my acceleration for my system, well, what's it going to be? So notice that I have positive tension here, negative tension here, and then g. So my tension disappears, and I'm left with m2g as the only external force acting on my system in the direction of motion, and I divide that by the mass of my system. And again, these three accelerations are going to be equal, so now you have a system of equations that you can work with. So again, the key to this is thinking about the summing up forces in the direction of motion, and really using the same equations over and over and over, but being clear. Really helpful to draw diagrams, and always when you have a pulley, it's always helpful to indicate on there what is the direction of motion that you're going to call positive. You can call either direction positive, but mark it and be consistent with it, and it'll all work out. Hope that helps. Talk to you soon. Bye.